This is Mrs. James. This is our end of course exam review session, and we're going to talk for a little while about the movement of heat energy. A lot of this will be review. You'll recognize it from junior high. Alright, in middle school, you should have learned that thermal energy is the energy of the movement of particles that make up matter. And I think that a lot of you are used to thinking that when something has a higher temperature, its particles are moving faster. When we start our class sessions back up again, we'll spend some more time talking about the difference between heat and temperature. For right now, though, we're going to talk about heat transfer, how heat moves from one place to another. And three terms you should recognize from junior high: conduction, convection, and radiation. Alright, so I know that maybe you didn't, or maybe you don't remember them, so we're going to review them briefly. Alright, convection first. Convection is this idea that warmer material rises. So material that's less dense, the particles are spread farther apart, are going to go up in the are going to rise, and the more dense, cooler material is going to sink. This you would experience if you were sitting around a campfire and you saw the heat rising from the campfire, and maybe you held your marshmallow a foot above the campfire, but it still got cooked. Well, that's because the hot air is rising. That's also why a hot air balloon goes up in the air, because of convection. Convection is a very, very important idea. It's critical to lots of things that happen in earth science, such as plate tectonics and the weather and ocean currents and food chains. Conduction. Conduction is when heat travels through material, often a solid, as the particles bump into each other. So as they bump, that particle bumps the next particle, and that particle bumps the next particle. It's kind of like dominoes when dominoes get knocked over. And it's a momentum transfer. And this would be what happens when you leave a metal spoon inside some hot soup. And the spoon gets hot too. That's called conduction. And the third is radiation. And the reason that we're discussing this now is that we just talked about radiant energy. So heat can also travel as a wave, just like the heat from the sun gets to us through outer space. So when radiation happens, heat waves travels. They don't need a medium. It can just go through the vacuum of space, just like light just like light does from the sun. And I see here I have traveling twice, and it has two L's once and one L once. Don't know which one is the right spelling, but I apologize for having it on there wrong. Alright, we learned in our electricity chapter about electrical conductivity. Thermal conductivity is very similar. Just like electricity can move through some things better than it can through others, heat can move through some things better than it can through others. We refer to this as thermal conductivity. If something is a thermal conductor, then heat can move through it very well. If something is a thermal insulator, heat can't move through it very well. Inside the walls of your house, you have what's called insulation. That is a thermal insulator. We don't want the heat escaping from your house easily, right? We want it to be trapped inside, so we use a good insulator. We don't want your hot chocolate to cool down too quickly. We don't want that heat to go through the walls of the mug, so we would build a coffee cup out of an insulating material also. Alright, the rate at which thermal radiation is absorbed or emitted by something depends on a lot of things. First off, whether or not it's already hot or cold. The second is its color. I think you're pretty familiar with this concept that black things absorb color well, and then that color is turned into heat energy. This is related to why a blacktop gets so hot. So the color black absorbs color and light very well. Different textures absorb heat energy better than others, and when you have more surface area exposed, more heat energy is going to be absorbed also. So when people are planning roofs and parking lots and buildings, and things are going to be outside, they really have to think a lot about things like color and texture and exposed surface area when they're planning. Everything is always either absorbing or emitting thermal radiation. If it absorbs more thermal radiation than it emits, and it's not evaporating, freezing, melting, boiling, so it's not going through a phase change, but it absorbs more than it emits, the temperature increases. If it's emitting more thermal energy than it's absorbing, and again it's not changing phase, then the temperature is going to decrease. So what do you think thermal equilibrium means? I want you to try and write your definition down here of thermal equilibrium. I want to pause the videotape, and I'll type in the answer in just a minute. When an object is maintaining a constant temperature because it is emitting and absorbing a matched amount of heat. Let's go over a few common misconceptions from our wave chapter. So this is everything that we've been talking about with waves. Number one, Doppler effect affects loudness. It doesn't affect pitch. The Doppler effect is what causes that sound that you hear when a race car goes by you. Number two, work can't be negative or zero. Let's ignore that one for right now. That's from a previous chapter. Ignore. Okay, particles travel with sound waves. Remember the picture that we had of a slinky. When a slinky goes up and down or back and forth, one ring of the slinky doesn't end up at the other end of the slinky, does it? The energy travels, but the matter stays where it is. It might go up and down, it might go back and forth a little bit, but it doesn't really move. Waves don't transfer matter, they transfer energy. This is true of light waves, it's true of sound waves, and it's true of water waves even. So as I talk and my sound waves travel through the air, the matter in the air molecules are moving around and they bump each other, and that sound wave eventually goes into your ear. But the sound waves, the air molecules in front of the speaker of the computer are not the same air molecules that go into your ear. So the energy travels, but the matter stays pretty much in place. Alright, destructive interference always destroys the waves involved. Remember we learned about destructive interference a few chapters ago. It doesn't, it might make it smaller, it might destroy it altogether. But remember that as soon as those waves have crossed paths and gone along their merry ways, the waves will come back. So that lessening of the wave during destructive interference is only temporary. It's only while the waves are in contact with each other. Wave properties are the same. No, they're not. You should be familiar with frequency, wavelength, and velocity. The two that are most often confused are wavelength and frequency. After that, frequency and velocity. Sound and light waves are the same. No, they're not. Sound is longitudinal, light is transverse. Radio waves are sound waves. No, they're not. A radio wave is a way that we send a sound from one place to another. So again, at the radio station, the sound is recorded. The machine turns it into a radio wave. The radio wave is then sent across the country, maybe across the world, where it's picked up by a receiver, and the receiver turns it back into a sound wave so that people can hear it. We couldn't make that sound wave travel that entire distance. It just wouldn't go that far, but the radio wave not only will go that far, but it will go really quickly. It will travel at the speed of light. This is also how astronauts can talk to each other in space. If an astronaut says something, that sound wave couldn't travel through empty space to another astronaut, but they can turn it to a radio wave. The radio wave can travel through the vacuum of space, and then the receiver inside the other astronaut's helmet turns it back into a sound wave. And the last one, infrared waves can be seen. No, they can't. You can feel them, but you can't see them. They are too long for the human eye to see. You also cannot see ultraviolet waves. You can't feel them either, but they will give you a tan. That means that you could go into a tanning bed in a very, very cold room that's pitch dark and still get a tan, as long as there was ultraviolet waves hitting you. Now that would be kind of freaky and strange and people wouldn't like it. So in addition to the ultraviolet waves, a tanning bed also includes some infrared to keep you warm and some visible light so that you can see what you're doing. And that is the end of this section. Next, we're going to start talking about waves and how they're applied to things off of our planet, which is the wave section of astronomy.